Hi everyone. This will be another test on the reactive generator here. Hi everyone. This video here is to further test the reactive generator. And the previous video we were testing to look at the prime mover, which is the induction motor there, how much power it uses while turning the alternator head. And we've determined that we can have the reactive circuit here hooked up and put it under load, and it has a zero effect as far as asking for more energy consumption from the power that's feeding to that alternator there. So I've left the setup identical here. Now that we've tested that side and we have concluded that there is no effect back to the prime mover of this generator, now what I've done is I've put my scope probes on the output here. So everything is identical. Nothing has been changed. It's tuned the same way. We have our same load that we have there. The only thing here is I've disconnected my ground here on the resistive load, because if I did connect this ground, what would happen is my reference ground here at the end on the return would actually be incorrect reading here on our current sensing resistor there, which is the same current sensing resistor. So we have just a small difference of 0.1 ohms from the ground from here to there. So it's a negligible thing, and our reading there should be very accurate as far as that is concerned. So now we'll be looking at the scope data once the circuit is placed under load. We're going to be looking at this side now of the generator, the output, and get the readings there. So I'll go ahead and start this. There's our watt reading, which is about the same as it was when I did the test, the prior test 2. This is test 3 now. And the circuit is off right now. And as you see, nothing is happening on the scope here. So I'll go ahead and turn it on. And there you can see the watts are fluctuating, but that's just the way the grid is. And here I can shut it off now. So there's just fluctuations. Anyways, it's tuned exactly the same. You'll have to trust me on that. I've not modified anything. Now what I'm going to do here is I'm going to display many waveforms just for now, because really to get an accurate reading of the real data, you really shouldn't be just looking at a single waveform. You have to look at the accumulation. And there is our voltage on our output there. So we're around just a little under 100 volts. That's because I can't, my induction motor is turning the generator at 3,500 RPM, and this generator to output 120 volts needs to be at 3,600 RPM. So that is the amount of voltage measured across our 0.1 ohm resistor. So that would be our current there. So multiply that by 10. And there is the math. So that is 8.97 volts. RMS is the math. And our means is 1.6 volts. And that is the voltage across our 15 ohm load, so 21.6, which that should come over 30 and a half watts of output. So now I'll change the voltage divisions here to get a closer look at the waveform. I know it's not very pretty, but that's this generator doesn't give out very nice sine waves. So there's our voltage here in the yellow. This is our current here, our current across the 0.1 ohm resistor. And the purple here is the load resistor, the 15 ohm load across that. And our math is there at the background. And as you can see, the data changes a bit as you expand, and I've been told that might not be the correct data once you have it expanded so much. I can give it even a closer look here. There is just one single waveform now, and that's what it looks like on the output side. So I thought I would share that as well, and I'll do another test and also try to combine that with this video here. Okay, we're back, and now what I've done with the setup is, instead of having a resistive load on the circuit, I've attached a induction motor on the circuit. And I have to do a 120 volt grid start on the induction motor to get it going. And if you remember on Valley's device, he also has to get it going on the grid. But once the RPM is established, then you can operate the induction motor on reactive power. And that's what I'm going to do here, is demonstrate that is also possible. So you see here one wire going to the grid, and that wire is coming to this relay, and this relay is going to be operated by this 12 volt battery here. And what we have is the induction motor is on the side of the relay that you could either flip-flop. It's always connected basically. So this side here of the relay is the grid. So once you activate the relay, the contacts will go to this side, feeding the induction motor just for a fraction of a second on the grid just to get it started. And then as soon as I release the contacts, it'll flip over to this circuit. So again, instead of the 15 ohm resistor, we're putting the induction motor in between where that 15 ohm resistor went. Nothing has been changed on the circuit here. Actually, I took out those two small 1 microfarad capacitors, and so that I can actually just drop the current. Now, this is a small induction motor. It's just like a half horsepower. And the DC or the resistance, well, a DC resistance in the coils is higher than what you would want for the ideal motor. The ideal motor, you'd want to have maybe like a 2 horsepower induction motor, where your coil resistance is much lower than this one. Because if you've got coil resistance, the reactive power will just burn out in that coil resistance, and you will have no work left on the armature there to turn the generator. So I'm not telling you that this motor here will actually turn that generator head at 3,600 RPM, because this is a 1,700 RPM motor. But it's something that I had here that I could just hook up and show you that it has a good potential of working. All right. So the idea here is that this induction motor would actually be turning that generator head. And if that generator head is placed under load through this circuit here, and you can actually make a motor turn, then there is a potential of looping this device. Now, this device that I have here cannot be looped because, again, I'm telling you, I don't have a good induction motor with a low DC resistance, and this generator head is only 1,000 watts, and on Valley's device he was using a 30,000 watt generator head that produce very high voltage, 600 volts. Voltage is also very important. So this device will not have a potential of being looped, I don't think it's possible. There's too much resistance in the coils of that alternator, and all the reactive power is being burnt out. This microwave oven transformer is very good, very low resistance primary coil. It's doing a great job, but where our power is being lost now is inside the alternator head. So that would have to be beefed up quite a bit so that the power wouldn't be wasted there, and this guy too. And then you have a potential of possibly looping this. So let me show you what happens when I just make a quick contact. So that's what happens. And that's all I'll be doing, is I'll just make a quick contact just to get that motor spinning, and then basically as soon as the relay flips to this side, and as soon as it flicks back to this side, automatically the circuit is connected at that point. And you'll see that we will maintain our RPM, which is, this is a 1750 RPM motor, and we will have very close to 1750. I'll do a tack check on there. So this wire here is feeding, like I said, inside my this side here of the panel here on the generator, and our induction motor is going to be working off the grid. So, and then let me tell you people also about the grid, is use it, okay, for experimental purposes only. We are not doing something here to connect to the grid. This research is about an alternator, a generator that's going to be working off of the circuit. We are not taking grid power and putting this through the circuit other than for experimental purposes. This is not a device to take power off the grid. Okay, I repeat that. That is not the research. And if you look at my titles of my videos here, it's talking about generator, a reactive generator. Okay, so it's about generators, reactive generator. It's not about finding ways of getting energy off the grid. So I make that clear, and I don't want to hear anybody saying anything more about the grid. So right now I'm going to be operating my induction motor off the grid. There is no circuit attached to that. We're using real power off the grid, which we are paying for. Okay, so all I'm doing here is showing you potential about how to make a generator work on reactive power. All right, so, and I'm giving you the possibilities here. I haven't done it myself, and I don't think I can, like I say, using these components. This plug here powers my isolation transformer, which is going to my oscilloscope. So we got three things here plugged, and then this is just a fraction of a second power just to get that motor turning, because you can't start a motor on reactive power, that's for sure. And then ideally also you'd want to be sending higher voltage inside this than the small 100 volts basically that I have, that I can get out of this thing. Even though this motor's made for 110 volts, once it's in reactive power mode, you can send much more voltage, and the more voltage you can send to it, my tests have shown that the stronger that the armature power or torque to the shaft would be. Because this motor here operating at 1700 RPM does not have much armature torque, okay, because of the wastes, like I'm telling you here. So it would take very little for the armature to stop turning. Okay, I'd just apply my thumb on it and it'll stop. So somebody else posted a video using a much larger motor. He's got a lot more potential than I have, okay, with this. But you have to keep in mind that those alternators here need 3,600 RPM for them to produce enough voltage for getting your circuit operating. So the scope is hooked up. We'll be able to look at what happens on this side of the circuit when the scope is hooked up. The induction motor turning the alternator head uses somewhere in the range about 165 watts. I will actually, through the way the circuit is tuned, maybe be taking about 4 watts more. So you might see it in the range of 169 watts or something around there. I'm just leaving it like that. I agree. I'm taking 4 watts out of the prime mover on this setup here. I'm not perfectly balanced. I don't really need to show that. You have your imagination and your experiments you can do, and that's about it. So let's start this generator here. So if you look, we're hovering somewhere around 165, 166 watts. The circuit isn't on. I'll turn on the circuit. This is what our waveform looks like. And there is our data. Alright. Now the induction motor isn't turning at this point. It is hooked up, but there's nothing that can happen until I can start this alternator off the grid. So what I'll do is I'll do that small little quick contact here and start the alternator. And now the alternator started. So it was just a fraction of a second just to get that alternator started. And to show you that it is truly turning, there you go. So it's turning at about 1740 RPM at the most. So it's pretty well there working. But like I said, I could stop the shaft, quite easily with my fingers here. But at least it's showing you that there's a possibility here, and that's all I wanted to demonstrate. Now, if we look at our waveform, it's changed because the induction motor, as it starts turning, will actually consume power. So that 30 watts that we were able to give out on the load is now being used, and you can see the current has changed here, and this is our this is our third probe here, where we had our 15 ohm resistor. That is now across the induction motor coils. So that's the amount of voltage going to the induction motor. Voltage that's measured across the induction motor coil, basically. So we have 45 volts there, and there is our math. So our means is pretty low. We're basically operating off of reactive power, and that is the amount of power running through the, that's the math calculations, and that is our current sensing resistor, our shunt. That is the millivolts running across there, then multiplied by our voltage. So we only have a small voltage, 103 volts. It's nothing. If we could actually push up the voltage to that induction motor, and I'll do a test simulation on that just off the grid to show you what happens. But now I just wanted to do it off the generator while I have this circuit all set up. So what I'll do right now is I'm going to reach over to the induction motor and stop the shaft, and you'll see what happens to the waveform. So I'm putting a little bit of a load now, so you see a change, and now I'll start adding more load, and suddenly everything collapses. Wow. What mostly collapses is where our probe 3, which is across the coil on the induction motor, as you see, the voltage collapsed against that, on that. So that basically now is just a circuit running through the coils of that induction motor and not really doing anything. So that's how that functions, and let me see if there's anything else that I can do. Oh yeah, I haven't showed you the power. So I'll start it up now. So again, it's functioning, it's working off of the reactive power. So the motor's turning now, and if we look at our input to our induction motor, as you see, I am taking 3 to 4 watts from that induction motor to the way the circuit is tuned right now. So that's about it for this test. And the next test that I'll do is I'll show you the motor, what happens when we use the same circuit but input higher voltage to the input here, but still utilizing this circuit here, and showing you that the benefit of higher voltage will give you more power on the shaft. So that's it for test number 2. And I hope this is helpful, and thanks for watching. Bye now.